So I know the title of this video is Substitution, but I want to be clear that before we get there, we got to talk about our three rules. And this is something I talk about in class quite often, but I want to articulate right now for everybody watching the video. Rule 1. What I do to the top of a fraction, I do to the bottom with multiplication and multiplication only. So multiply top and bottom fractions. If I have xy and I multiply top and bottom both by 3, it's still equivalent to xy. If I multiply the top and bottom by the variable a, it is still xy. And if I multiply by the sum, a plus b, as long as it's treated as one thing, it is still xy. That is rule 1. Rule 2 is what I do to one side of an equation, I must do to another. We've been solving equations, one step, two step, multiple step, doesn't matter. Somebody just texted me. And if I do this, you notice they stay true. And then rule 3, and this is the big one today. If I have 4, I can replace it with 5 minus 1 because they're the same, they're equivalent. I can substitute 5 minus 1 in place of 4. And equivalency covers all the rules of exponents and lots of ways we do math, alright? But this is the rule we're going to concentrate on today when we talk about substitution. And it has to be equivalency. So, I'm going to start with an example here as we work forward. What if I have the expression x squared y over p? Alright? And I say x is 2, y is 4, p is negative 1. Most of you guys wouldn't even pause. You'd start to evaluate this immediately. Because what's equivalent to x? Well, the numerical value of 2. What's equivalent to y? 4. What's equivalent to p? Negative 1. And then all of a sudden, it becomes an operation problem. Well, that's equivalent to negative 16. When you put the numbers in, that was substitution. You replaced a variable with something equivalent. They were the same. So if a equals b, then a can replace b. X equals 2. You can replace x with 2. Actually, you could also replace 2 with x. That's the vice versa. So what's that mean? Well, that means we can do some things. Before I get there, I want to start with, hey, we have two equations and we have two lines because we have x to the 1 power, y to the 1 power, 1 equal sign. This is a line. And on the next slide, I actually grab it. This is a line. So I start with the question, is the point 3 comma 5 when x is equal to 3 and y is equal to 5, is that on the lines? Which of these lines is that on? If I plug that into this equation, 2 times 3 minus 5 equals 1, replace x with 3, y with 5, and over here I do the same thing, 3 and 5. We find that over here I get 6 minus 5 equals 1, or 1 equals 1, so this is on the line. The equation is true. Over here I get 3 equals negative 4, which that is false. Therefore it's not on the line. Then I pick another point, 5 comma 2. X is 5, y is 2. Plug it into the equation. And again, x is 5, so I'll replace x with 5, and I'll replace y with 2. And I find that at the left side, it's not on the line. Over here I find it is on the line. And you notice I put at the bottom, big deal. It is a big deal. Now, while this point is on this line and this point is on that line, there is a place, most likely in this case, where the two lines cross. And often in the real world, that's a line of profitability versus how many workers, stuff like that. And there's these optimum points where lines cross. So that's what we're talking about today with substitution. Because if I take these two lines on the next board and I graph them, A is the top line, B is the bottom line. And I graph them, and we've been graphing, you take my word for it, this is the graph. You'll notice that point P is on line A like we talked about, which is 3, 5, and point Q is on line B, which is 5, 2. But there's this point right here, which I'll call point capital I for intersection, that we're going to be very interested in mathematics. The question becomes, how do we find that point where those two lines share a true value? Well, I look at here and I have these two equations, and on equation B you notice x is equivalent to all this stuff. Well, I am going to substitute for x. I'm going to substitute b into equation A. And what I mean by that, if I write A, 2 times x minus y equals 1. And you notice I put parentheses around it because here's what I'm going to do. I'm going to say, hey, I have x, I have y. What can I get rid of? Well, up here, x is exactly the same as that stuff. So I'm going to replace x with minus 3y plus 11. And if you can't hear my cat's crying here, it's because she is so excited about what we're doing. And here I am, and now I'm excited because now I have one equal sign, and all of a sudden I had two equations with two unknowns. Now I have one equation with one unknown. And that's the key. We can solve for this. I'll distribute. I'll combine like terms. And then I'll move the 22. And I'll get negative 7y equals negative 21. Divide by negative 7. And y is equal to 3. I just found the y coordinate. But listen, I don't want the y coordinate only. I want to know the x and y. So how am I going to find that? Well, I got equation b here. It's nifty. So I'll write b is equivalent to x equals negative 3y plus 11. But now I know y is 3. And if I start graphing this and do the math fast, negative 3 times 3 is negative 9. Negative 9 plus 11 is 2. So now I got x is 2, y is 3. Well, that's an ordered pair, 2 comma 3. That is the point. That makes both of these equations true. And if I go up to the graph of these two lines now and I take a look at 2 comma 3, 2, 3, you can tell that's point I on my graph. And that's a powerful point for us to find in math. And this method is called substitution. Because we substituted for a value. Now, these are complicated. These take a lot of practice. So I'm going to show you a couple. And we'll be working on this quite a bit. And I have another two lines. Again, I know it's a line because it's an equal sign with x and y to the first power. The bottom one is x and y to the first power. So I have line P and line Q. And those lines most likely are going to cross. There are times they don't cross. But right now they're going to cross. And we want to know that point of intersection. And I see that y is by itself in equation Q. So Q is self variable y. So if I write, I'm going to put Q into P. And if I write equation P with x and y, what can I replace this time? Well, this time y is solved. Y is equivalent to all this stuff. So I'll put all that stuff in there. And again, yippee! One variable, one equation. If I solve this, and again, I can do it quite a bit faster than you guys. I'm well practiced. Now, sometimes we get to obvious equations at the bottom. 5x equals 5. I still take the time to make sure I divide. Because often when we think they're easy, we make math mistakes. X is 1. Now, a lot of times students feel, yeah, I finished. But remember, these are lines. They cross. I need an ordered pair. So I take the 1, and I see that y is equal to x minus 6, so I use Q. And I'll substitute right away. Here's x, minus 1 minus 6, negative 5. You must always write the point as an intersection point. 1 comma minus 5. Now, on the next one, before I get started, if you want to try these, I have two equations here. Alright, you want to write them down and try. I'm going to show both here. But again, I have C and D lines over here where x is solved, and I have A and B lines on the right example. So I'm going to work the one on the left first. Equation C, 3x plus 2y equals 3. X equals 3y minus 10. You notice that D is already solved for the variable x. So I'm going to put D into equation C. And I have 3 times x plus 2y equals 3. And again, you got to see it here that these are the same, except I replaced x with 3y minus 10 because they're equivalent. Now I have 9, I distribute, I combine like terms, 11y minus 30, add 30 to both sides. You get 11y equals 33, which all of us know means that y is 3. I use the equation D. I could have used equation C. If I use C, it will still work because both lines are true. If I use equation C, it's just a little more work is all. I should have done this before the video started, but you have to notice because both lines are true, both methods work every time. Both equations result in the same ordered pair. And again, you solve for x, you get -1, you get a point of -1, 3. These cross in the second quadrant. On the second example, I got a equals y, or line A, sorry, y equals -3x plus 8. Line B, -x minus 2y equals 4. Again, two lines, x and y to the first power, equal signs. Two equations, two unknowns. That's going to become a real big deal for us. That means we can solve it. If I had 3 equations, 3 unknowns, I could do it, 4 and 4, so forth. But it's going to take a method. So this time we're going to substitute again. And I see that A is solved for y. So I'm going to put A into B. This time I rewrite B right here at this point. And I say, hey, I know that y is equivalent to -3x plus 8. So I stick that in place of y. And again, every time we do substitution, we have to do parentheses. I distribute the -2 and make sure my signs come out correctly on the distributing. Combine like terms. Get 5x minus 16 equals 4. Add 16 to both sides. 5x is equivalent to 20. Divide both sides by 20, or 20, by 5. And x is 4. Again, I'll use A because A is easier. I could use B. It will give the same answer. I plug in 4. I get -12 plus 4. I get y equals -4. These points cross at point 4, -4. That's in the fourth quadrant. And again, these are optimum points for math. This is called substitution, solving by substitution. We have two equations, two unknowns, and we're replacing one variable. In this case, on this side, we replaced y with all this stuff. On the other side, we did x. It doesn't matter which one we replace. This takes practice. This is one of the most important things we'll cover the whole entire year.